Hi folks, we're going to take a look at number 9 on page 415. So here we've got a parallelogram, OBCA, with these two sides given by the vectors A and B, and fourth vertex, as given here, is just C. All right, and then they give us some information. But let's start by drawing the parallelogram. All right, so let's say this is point O, and say I'm going to point A. Okay, and then here this will be O to B. So this is vector A, which is 4, 2, 4. And this is vector B, which is 3, 1, 4. All right, and then we'll finish off the parallelogram here to point C. All right, so this is our scenario. So let's see what's going on. So it says that a line is drawn from B perpendicular to the side AC. Okay, so that it intersects at N. So essentially what we have is we have a line that's being drawn perpendicular to AC, meeting at this point N. All right, so right angled. And they want us to determine the length of this side length BN. Okay, but just to put in context for what we normally use is we see that this length BN is just going to be the magnitude of the vector BN. So that's what we're looking for. All right, so there's a couple of ways to solve this. So I'll talk about the longer way. That's maybe the more direct approach. It's not the one I'm going to take. So I suppose what you can do is see that this is a right angle triangle, and you see that the vector BC is the same as vector A. So in other words, the magnitude of this vector would just be the hypotenuse of that triangle. And because it's a parallelogram, this angle inside the triangle is the same as this angle across it, which of course is the angle between the vectors A and B, and you can use a dot product to find that angle. And then once you have the hypotenuse and this angle, you can just use right angle trigonometry to determine BN. And that's a perfectly valid way of solving this problem, but I'm going to use, I think, a quicker method here. And it all comes down to recognizing this length BN as being the height of this parallelogram. All right. So if this is what we're using as the height of the parallelogram, then AC, which is equivalent to vector B, would be the base of the parallelogram. And of course, we now know that we can find the area of this parallelogram by just taking the cross product of vectors A and B. All right, so that's what I'm going to do here. All right, so the height of the parallelogram that we're going to use is what we just talked about. It's the length we're looking for, the magnitude of BN. All right, the base length of this parallelogram is just the magnitude of vector B. Okay, and what is the magnitude of vector B? Well, it's just going to be the square root of 9 plus 1 plus 16. So that's 10, so root 26. And then the area of this parallelogram is just going to be given by the magnitude of the cross product A cross B. And then from there, we'll be able to easily calculate the height, since, of course, the relationship is that the base times height is equal to the area. So let's do this on the side here. So I've got A cross B. So I've got 4, 2, 4 crossed with 3, 1, 4. Okay, I'll bring my 4, 3 over to the side. All right, and let's calculate the cross product. So cross product here. So first we're going to start with the y's and z's. So here we have 8 minus 4. So that's 4. Here we've got 12 minus 16, negative 4. And here we've got 4 minus 6, negative 2. So if I'm looking for the magnitude of this cross product, it's just going to be the square root of 16 plus 4. And this is 20 plus 16, 36. Oh, that actually ends up being nice, that the area is 6 square units. All right. So now I'm just going to use the formula. Area is equal to base times height. Okay, so our area we already determined was 6. Our base we determined here was root 26. And the height, of course, is just represented by that length that we're looking for. So the length of BN, which is just the same as the magnitude of the vector BN, is just equal to 6 over square root of 26. Okay, and I think this is a little easier, a little quicker, even writing out all the steps really explicitly than our original, more geometric approach. Okay, so here we use the fact that the cross product of two vectors placed tail to tail gives us the area of the parallelogram formed by those two vectors. All right, that's it for this one.